Yeah, screen sharing hides those things. It's tough. It's those college board videos we were doing, we have to mute ourselves at the end, and sometimes I'd have a hard time finding the controls to be able to mute myself. All right, says we're
Good
recording.
morning, everyone. Good morning. I am Monique Rice, Senior Content Director from Advanced Kentucky, and welcome to our AP Calculus Content Review session on series presented by Mark Curley. Um, we intend this for a Kentucky audience, but we're happy to have students from all over. Just know that we'll be keeping an eye on you, and by we, I mean me. But I don't expect to have to worry about anything here in this disclaimer. Uh, Again, I am your host. I am the content director for computer science, which means basically I lead the computer science programs, but I am a former question leader reader for the AP Calculus exam, so I'm excited to get a little calculus in today. Everybody's microphones will be off. Please feel free to use the cheat, not the cheat, the chat. See, computer person, I got cheats in my brain. Um, Use the chat to ask questions and the like. Your videos will remain off, and make sure you can find that chat button. Mark, if you want to open up microphones at any point, all you have to do is say so. We're
Okay.
not going to be that strict for the
As I said, we have
fiduciaries
such a
here.
small group. I'm okay with you giving them the ability to turn their mics out if they need to.
Yeah, turn the mics on. Um,
If there were
and a
50, you know.
recording. Yeah, no, right. The true cacophony of noises, right? Recordings, links to handouts, and information for all future content review sessions. Not gonna be many more. This is May 1st, so uh, it can be found by visiting the bit.ly link that you see there. So I am going to stop sharing now,
All right.
and Mark, take it away.
Yeah, and I had put in the chat, just curious if people are students or teachers. I'm going to treat you like your students anyway, because as Monique said, this is intended for students, but I do understand that as a teacher, they're very valuable as well. So let's see, there we go, got that minimized up. And I lost my chat just as we were speaking of losing controls.
I got the chat if you
Oh, there it is.
want to learn something.
Yeah, I just like having it in my second screen. So there we go. Okay, so um, I'm basically going to treat this like it's May 1st. The test is May 4th, and you're my kids, and you have just missed. You know, you somehow it wasn't the last month, but when I did series, you missed it. So I'm going to start it like I started. The nice thing is Brian did a lot of legwork for me last week, but this is actually where I start my unit. I actually start my unit with Taylor polynomials, and if you want a guide on that, if you Google Ben Goldstein, he has a chapter he has put out for free. It's not from an actual book. It's a standalone chapter he's wrote, and it's a real good guideline. I don't use it, but I reference it. He builds with polynomials first, and um, builds up to convergence series, and then the infinite series. So we're going to jump into our warm up. We get a little full screen for you, and the title here is kind of covering what 1011 through 1013 cover for me. It's Taylor polynomials, which we're using to approximate functions that maybe we can't find exactly. And then the second one, 1014, is Lagrange error bound. It's how close can we get? And then 1013 is your radius of convergence and your interval of convergence, which is when does this polynomial work? So it's all about the approximating for this first hour. It's here's my polynomial. How close can I get? When does it work? So here's my warm up. And it's given the second derivative of y with respect to x is 4. Find an equation for y equals f of x, and you're also being told that y prime at x equals 0 is 2, and y at x equals 0 is 5. And I'm going to mute myself because I'm horrible about talking while people are working, and I'm going to give you a minute or two to work through this warm up. And 2 minutes is a long time when you're just sitting there staring at the screen. All right. Hopefully that gave you time to at least get a good start, if not finish the problem. I'm going to slide my camera up into screen here, and I've just copied down the information. So this is a first semester, AB or Cal 1 question, really traditional. Second derivative is 4. So the first derivative is 4x plus c. I do have this 0.02 for my first derivative. So I can plug in 0 and 2, and I can see that c is 2. So dy dx is going to be 4x plus 2. Man, my school teacher instincts kicked in there. I almost hit the admit, and fortunately I have an assistant today. And then take the antiderivative of that, and y is going to be 2x squared plus 2x. If you see me make a mistake, please jump in. The mic should be live. This is plus c, and then I can get that c is 5. And so I get this quadratic formula with, or not quadratic equation, sorry, quadratic function with the attributes that I was asked to find. And the reason I like to introduce this is I probably taught BC, oh geez, I don't even know if I want to admit how long, maybe 5 or 7 years. And these problems were in the first half of the textbook that I was teaching out of. And I always assigned them because I thought they were neat. I thought they were kind of puzzle-like. It never occurred to me that the author here was setting us up for Taylor polynomials. And I was like, when it dawned on me, I was like, oh my gosh, we have to tie this back. So, for the students, I always tell you guys, don't talk to people who took Cal 2 last year and didn't take the next course about series. Don't talk to your aunts and uncles, your parents. If they stopped after Cal 2, do not talk to them about series because they never got to use them. And if you talk to math students, whatever the last thing they learned that they never got to apply was, they tend to not like it. The pre-cal kids tend to not like the trig identities. The algebra 2 kids don't like rational functions, or wherever they ended up, or logs, or whatever their last unit was in their algebra 2 course. And then when they start using them later, they just become one of those other tools in the toolbox, and they don't worry about it. So first off, there's that. The BC kids leave not liking series because they never got to see them really applied. The second thing is I don't think we always do a good job of tying it back. And so one of the things I want to do for the students is tie it back. And I want you guys to realize that we've been doing this game for a long time. We do the tangent line approximations. Well, this is a quadratic now that applies that can approximate a function with these attributes. I don't know the second derivative is constant. I just told you the second derivative is 4, and then we worked it back. This thing may be a function that has infinite derivatives, like something with e to the x and something else in it, or a sine or a cosine, any of the trig functions. But what I do know is I can evaluate the second derivative at a point, the first derivative at a point, the function at a point. And now, not only is this tangent to the curve at the point 0, 5, it also has the same concavity for that instance, as well as the same slope. And I can even go farther. I can make sure that the curvature of the concavity and so on. So that's what Taylor polynomials do. They approximate functions better than a tangent line. And the farther we go, the better they approximate them. Go back to my slideshow. I'm not going to reteach the whole unit for you, obviously, but this is another warm up. I think I'm actually going to not take the time to if you want to pause the video, if you're watching this recorded in the future, if you want to get a head start, but this is given a third derivative, it's 6. And now find the second derivative, and I'm sorry, yeah, given the second first, and fucking, I need some more coffee. Given the second first and the function at a point 0, find the equation. Just take a little sip of coffee and get my camera ready, and while you start the legwork on this problem. All right, well, move my camera up so if you've gotten a little bit of start on this. So my third derivative is 6. So my second derivative is 6x plus c. We're going to plug in that 0, 4. And then my f prime is going to be 3x squared plus 4x plus c. But again, I'm doing it this is 0, which makes these things really nice when I'm dealing with polynomials. So my f prime is 3x squared plus 4x plus 2. And then my f, let's see, x to the third plus 2x squared plus 2x plus c, which is at f of 0 is 5. I'm just going to put the 5 there. But you'll notice that adding that third derivative did not change the quadratic term, the linear term, or the constant. In fact, if I want to write this in a more traditional Taylor polynomial way, instead of a traditional algebra 2 polynomial way, if I put the exponents counting up, I start to build this idea of there's my f of 0, there's my f prime at 0. There's my second derivative. My second derivative was 4, though. So that's my second derivative divided by 2. And then my third derivative was 6. So that's my third derivative divided by 6, which of course is 3 factorial. And so I like to do, like I said, we're not going to introduce the whole thing because you guys are here for a review session, but I just want to kind of point out where these things are coming from, that you can build this whole idea. And this is what you guys need Tuesday. You need to have that idea coming in. So if you have really not memorized that form of the Taylor polynomial yet, that's your job for this afternoon. I would say before you go work on any more practice, because here's our big mess of an idea is that we start with, what if we assume the polynomial, right? This is our polynomial, general polynomial centered at C. But this a sub n is always going to be your nth derivative divided by n factorial at the center. And so these are your prettied up forms of it. And if it's a Maclaurin series, C is 0. Those clean up really nice, like the one I was working with. But even without it, it's not bad. And you just got to remember, 0 factorial is 1. You'll notice over here. So it's the same pattern every time. F of C, 0 factor, x to the 0 is 1, as long as x isn't 0. And actually, if you go look in the textbook, they even say we're going to let 0 equal 0 for Taylor polynomials. We've got our 1 factorial, x minus c to the 1, 2 factorial, x minus c to the 2. It's the second. And, these all match up, right? Nth derivative, n factorial, nth power. If you memorize that, we could randomly go pick a BC question from the past right now, go find a BC6, and you can get anywhere from 3 to 5 points on a problem just knowing this and using your calculus intuition. And so that BC6 problem shouldn't be scary. That BC6 problem is like, this is a chance to get points. There's a lot of opportunities there to get points, and there's opportunities with different chunks of knowledge. So like I said, this is your afternoon practice, is this bottom line. Is I would have that memorized. If you have that memorized, then you should practice using it. And these slides are available in that folder. Again, I just wanted to lay some groundwork, and then we're going to get in some practice problems here in a few minutes. The radius is how far from the center will our approximation work. The polynomial is not going to be perfect. So I have to know how close will it work, because at some point it's going to break off. In fact, we can look at a picture of that in a little bit. The interval is just the radius to the endpoints, and I don't know if the endpoints are going to work. So we use the ratio test, and what we're doing with the ratio test is we're pretending this thing's acting like a geometric series, which Brian talked about last week with convergence of geometric series. And so we look at the ratio of one term to the other. If it's geometric, this term right here, and I'm gonna actually turn on my laser pointer so I can make sure. I was gonna try and turn on my laser pointer. There we go. This one right here, if it's a geometric, that's constant. And then it's just straight up less than 1, it converges, 1 or higher, It doesn't. So we say, all right, let's make it less than 1. Let's find this ratio, and then we'll know where we converge. The problem with it equaling 1 is if this is a constant equals 1, it's not going to work. If it's a limit and approaching 1, it depends which side it's approaching 1 from, if it bounces back and forth. And that's why the 1 is inconclusive. And when you set up your ratio test, we get this question a lot from students. They say, can I just take the n plus 1th term and multiply by the reciprocal of the nth term? And I would actually prefer that. Instead of writing that complex fraction with the 4 levels, because these are usually ratios, with this ratio over another ratio, you absolutely can just reverse and reciprocate that a sub n. And then there's the Lagrange error bound. And by the way, I know I'm going through these slides fast. I'll refer back to them. This is the way I do notes in my class sometimes. I want this here as a reference, and you've got a link to these slides. So, and actually, you know what? I'm going to look at my first exam. We are going to come back to Lagrange error bound, because I just threw a lot of information at you if you're coming here to finally catch up on this information. So go back to my viewer, because I also want to stop talking. I can talk forever. Let's get you guys reading and looking at some math. All right. For number 1, I'm going to go ahead and use this screen. All right. And the numbering system on this handout, M1 means I rewrote an old problem. I may have even completely rewritten it, but M1 means Mark generated it. Some of you will recognize them from practice tests you've taken over the last few weeks, but I've moved some numbers around. Anything else that has a regular number next to it, I took from a source, and I've cited the source, and it's a publicly available source. So we have the function f has derivatives of all orders for all real numbers. F of 3 is -2, f prime of 3 is 5. The second derivative at 3 is -6, and the third derivative of 3 is 24. Using the third degree Taylor polynomial for f about x equals 3, what is the approximation of f of 3.1? And I'll give you a second to play with that. While you do, I'm going to point out this is the only calculator active problem in the entire packet. These tend to be on the non-calculator part. I think there's 2 reasons for that. I think it's even if they're in the calculator aloud, the calculator doesn't help most of the time. And I think they usually don't take the 3 minutes. They like to save those 3 minutes for theorem questions. And if you don't know what I'm referring to there, the calculator problems, you have an average of 3 minutes a problem to work on. In the non-calculator, it's 2. Okay, gonna give you a kickstart if you haven't started. If you've started, this will be reassurance. All right, they didn't give my polynomial a name. I'm gonna call it P. They want it to be third degree, and it's centered at 3. So this is that formula we were just talking about. So f of 3 plus f prime at 3, and that's technically divided by 1 times x minus 3. My second derivative at 3 divided by 2 factorial, which is really just 2, x minus 3 squared. And I stop. Oh no, gotta go to the third degree. Third derivative at 3 dividing by 3 factorial, x minus 3 cubed. All right. So that's your jump start. And then they want to know the approximation at 3.1. And this is an approximation. A lot of times you'll see f of 3.1 equals p is approximately equal to the approximation symbol. And I'm going to go ahead and put the 0.1s in there. Ooh, let's go ahead. We can insert all kinds of stuff. I know f of 3 is -2. I know f prime of 3 is 5. Second derivative is -6. And these all become 0.1s because 3.1 minus 3 is 0.1. 24. I'm going to go ahead and call the 3 factorial 6. Although I'm using a calculator, so if I wanted to use the factorial, I could. It's just it's buried in menus. And then if it wasn't clear, this was a calculator active problem by the choices and the fact that I mentioned it. At this point, you become very hopeful that it is. Oh, and I think I can Julia Child this. I actually typed it in last night. So I've got -2 plus 5 times 0.1 minus 6 times 0.1 squared plus 24 times 0.1 cubed. I get -1.536, which is my choice D. Or wait, hold on. Did I make a mistake? I did. I tricked myself. That was when I was generating the wrong ones. That's what I just did. 24 divided by 6 is 4. C. Sorry, Saturday morning snuck up on me. There we go. And we're not going to go through every problem in the packet, I'm sure, but I am going to send solutions to Aaron Timmons, and he will get those up in the folder sometime this morning. So yeah, C for more coffee. Thank you, Mary. I'm so sorry for those of you that I panicked. I should have just gone and typed it in. I got too excited when I saw work on my calculator. You should never trust the calculator. All right. The next one, I'm actually, my printer did not like the image file, so I'm going to slide over here to screen number 3 and pull in. Okay. So, and this is, this is what I do in my classroom. So students, if you're seeing this and wondering, wow, he jumped into problems fast. I love the Taylor polynomial because of how many points it accesses for you guys immediately. You don't have to worry about all those convergence tests yet. You don't have to worry about interval of convergence. There's points to be had just with this. And I think that's such a powerful tool. So let's look at this one. This came from a course and exam description, which are things they provide to the teachers to let us know what's going to be tested. It says the 3rd degree Taylor polynomial for the function f about x equals 0 is t of x equals 3 minus 4x plus 2x squared minus 3x cubed. Which of the following tables gives the values of f and its first 3 derivatives at x equals 0? Again, I'll give you a little time to digest that. All right. Lost my, there we go. So I moved my camera around to manipulate the screen here. So I'm looking for f of 0, f prime of 0, f double prime at 0, and the 3rd derivative at 0. And it's the same idea as we're just going backwards. We've got, they gave me this idea that this is my function. That's my f of 0. That's f prime. I'm going to not write the of zeros. That's f double prime over 2. And that's the 3rd derivative over 3 factorial. So f of 0 is 3. F prime is -4. I can read those straight off it. You could also take the derivatives. You could also sit there and take the derivative of this polynomial 3 times. And those are all going to match up, right? Because that's the whole idea is we set this 3rd derivative equal so that the 3rd derivative, 2nd derivative, 1st derivative, and the function value are all the same at that single point. And then we can use that to approximate. So the 3 and -4, and that all that does is that eliminates choice A for me. If I think about A, B, C, and D here, I can cut A out. The 2nd derivative is not 2. It's a number divided by 2, which is 4. And that's going to cut B out. And then D, -3. So we're saying -3 is what? over 6. And so my third derivative is negative 18. And that means we are at choice C again. And the really savvy kids notice, oh, hey, every single third derivative is different. I'm just going to find the third derivative first. And there's part of me that likes that, and there's part of me that would still not trust it and want to go back and reconfirm them all. The reason I prefer doing it the way I modeled here is they can give you a polynomial that's huge, or they can give you each term is described by and give you a formula, and then ask for like the 30th derivative. Well, you don't want to go through this process of taking the derivative every time. So we have that general term. And the general term looks like this. This is that's your general term of your Taylor polynomial. And if they ask for the nth derivative, then you just go find that coefficient. Somewhere there's going to be an a sub n tied to x minus c to the n. Find out what that, if this is the 30th, if I said 30th derivative, I go find the 30th power, find the coefficient on the 30th piece, and then it's always going to be that number times n factorial. So my 30th derivative is just 30 factorial times a sub n. And normally they'll have it left as 30 factorial because nobody wants to go get the scientific notation number for that. But then you get really good at that. And you're like, okay, so it's 2 times that, 6 times that, 24 times the next. And you can start building your derivatives very quickly. So with that in mind, here's a very similar problem. And I apologize for having the settings open on my camera, but they sent an update down this week. And if I turn the settings off, it's very jumpy. But for some reason with the settings on, it's very smooth. So I'm calling that a feature. I also have this ability to have a second window, which is, I'm sure I'll find a use for at some point. All right. So same type of idea, except we're going backwards, right? They've given the table and they've given different values. And now I want to look specifically at the fact that they said at x equals 1. And so my f prime of 1 times x, right? F of 1, double prime of 1, x minus 1 squared over 2. And my third derivative at 1 over 3 factorial, x minus 1 cubed. So a's gone because a is clearly centered at 0. So, but they used the values of f of 1, so that's a hint, huh? All right. First and second derivative don't differ at all. If I look over here, I'm looking at 2's and 3's. Let's see, my second derivative is 3. So I should have 3 halves x minus 1 squared. So that gets me down now to
Hey,
B
Mark.
and C. Yes.
Mary has pointed out that on term 2, you have an x that should be
Thank
x minus
you.
1.
Thank you. It's because I started with f prime. It like threw me. Thank you, Mary. And then my third derivative is going to be -2. 3 factorial is 6. This was kind of an evil distractor because if the student forgets that factorial, they might choose C. But we finally got a non-C answer. We got B. All right. So, and hopefully that gives you a little bit of confidence, because these are all, even though they're coming from course and exam descriptions, these are all problems that were written by people on the development committee. They're chosen for these documents for a reason, to teach us how to do things. So hopefully that's a really good sign that on Tuesday we're going to see similar problems. And now we're going to talk about radius of convergence and interval of convergence. If I can get this window to grow for me. There we go. And I've got what is the interval of convergence for the power series as n goes from 1 to infinity of -1 to the n plus 2 over n times 3 to the n times x minus 4 to the n. And there are some tricks of the trade to this. I do want you to be cautious. And I know if you guys watched any of Brian and Tony's videos this week, I had my students watching them, and I know they talked about a trap here that you need to be aware of. So I am going to set up a ratio test for this one, although I do want to point out this one, you really don't need to, but I just want to show it so you can have the practice, because on a free response, they'll say, show the work that leads to your answer. But if you look at those answer choices over there, and I look at my series right here, I've got that x minus 4 to the n. I know my center's at 4. So A and B are gone. C and D, the endpoints are the same. So I know my endpoints are going to work. I know my endpoints are going to be 1 and 7. And then the only difference is whether 7 works or not. So what you're really going to end up doing on this thing is testing x equals 7 and seeing if you get a convergent series or not. But I want to go ahead and just do a practice setting up a ratio test, because this is a lot of points when it happens on a free response. So we're going to use this as a practice for free response modeling. So this is just our end game is going to be that x minus 7 or x equals 7. So my limit, and the first thing I'm going to do is its absolute value. You know, I know that -1 is going to go away, but I want to show it. If I'm being graded on a free response on show your work, then I'm going to put all of these guys in here. That n's being replaced with n plus 1. I've got x minus 4 to the n plus 1 all over. Now, I'm sure someone's going to ask, do you need the -1 to the n plus 1 to get full credit on the free response? Probably not. I mean, that's the readers know it's an absolute value and you're not writing anything false by eliminating it, but it could catch you later if it's -1 to the 2n or something like that. It's going to be important. So this is my original with just n plus 1s at every single location. Sorry, I'm pointing at the paper that you can't see. So I have an n plus 1 there, n plus 1, n plus 1. I did slide the x minus 4 and the -1 up into the numerator. And then I'm going to multiply by the reciprocal of the original, which is the same as dividing. This is that 1 over a sub n. So I have n times 3 to the n over -1 to the n plus 2, and x minus 4 to the n. And I set that less than 1 because I need it to be less than 1 for this to converge. I need that ratio to be to be getting smaller and heading towards 0. And then we're going to just start cleaning up. And at this point, I am going to just knock these -1s out and ignore them. And actually, this is a question. This is actually a really savvy question. If anyone's ever asked this, we make a big deal at the reading that you guys can cross out work. And that's the same as erasing. It actually says it on the directions to the test that any crossed out work won't be read. And I've had people ask me, well, if they cross all this out, do they get to set up the ratio test point? We're all mathematicians. You know, they've had people like Monique and myself grading these things. We understand the difference between canceling and crossing out work. You're not saying it was never there. It's part of the process. And so know that drawing a line through it in this case doesn't mean it was never there. But it looks like I'm having n plus 3 on top and n plus 1 in the denominator. So I should say numerator, I suppose. And then I've got one more x minus 4 on top. So those are all going to cancel except for one of them. And I could do that with subtraction of exponents, n plus 1 minus n. I've got an n there. That's going to stay. I can't do anything with that. But I have one more 3 to the n on the bottom than anywhere else. I'm going to have a 3 left over because n plus 1 minus n and keep it where there were more. And I still have that n plus 2 down there. And I could jump to the answer on this one, but I'm just going to clean it up. I'm going to get all the stuff that does not have an n together and all the stuff that has an n together, just so I can see what's happening. And so I've got this limit as n goes to infinity of x minus 4 over 3. And then I have this rational function in terms of n, or rational expression in terms of n times n squared plus some other stuff, n squared plus some other stuff. And so I have a second degree over a second degree. It's 1n squared over 1n squared. That's going to go to 1. That's n behavior of a rational expression. You can just claim that's 1. You've probably been talking about those since algebra 2. Maybe not in limit context, but in terms of as x gets really large or small. So I'm going to have x minus 4 over 3. And in terms of scoring on the AP test, I've just earned 2 points usually. 1 point for setting up my ratio test, 1 point for finding my limit. The limit can go away. There's no n's left. Yay. It's not wrong if it's there, but it's kind of silly. And then I can multiply that absolute value of 3 out, which is 3. And now I can see my center and I can see my radius. If you're asked just to find the radius, and sometimes they will ask you this, they'll say, find the radius. This expression is not enough to find the radius. It's going to get you those first two, but you have to declare your radius. You either off to this, do what I did, or say radius of convergence is 3. Or I mean, you could box it, but I wouldn't take my chances with just a simple box. I would label it, or even better, just a small phrase, radius is 3. And then that means I know I'm going from -1 to 4 to 7, which matches the work here. 3 minus 4 is positive 1. 1 to 4 to 7. And then I have to test the endpoints. I don't know what's going on at the endpoints yet, which brings me right back to where I should have been on the multiple choice. If we addressing this problem, 7, I'm going to plug 7 in for x. These are values of x, right? That is a true statement, but I want x where that 4 is. Geez. Glad I'm not taking the test Tuesday morning. I need to be in the afternoons, apparently. And this one starts at 1, correct? Okay. So I've got 7 minus 4 to the n. Well, that's just 3 to the n. So those cancel. So I'm going to have an alternating series. But part of alternating series converging is the terms have to go to 0. These terms go to 1. So this diverges. And it's going to be choice C. Right? Man, it's C a lot. I wonder if that was intentional. All right. Any questions about that? And again, this is your end game for this problem, but I wanted to model for the free response because we've got a limited amount of time and I'm not going to do every problem on here. So. All right. I did mention a trap that Brian had mentioned. We'll come back and catch this number 3 in a second. Here's a radius of convergence problem. Let's see, what was that, Monique?
So when you write multiple choice questions, especially if the answers are numerical, they want them in some sort of order.
Right.
And so it's really hard to get answers that aren't B and C. They tend to be B and C. Yeah. Because they either want them in some sort of ascending or descending. Yeah, they have to be ascending or descending, or if they're equations, they want them to grow or shrink. They don't want it to be disjoint. Yeah. There's very specific rules for the multiple choice writers. Yeah. Yeah, and they've upped the game on the rules for algebra mistakes too. You're not allowed to have algebra mistakes as the distractors. So it's like it has to be a calculus mistake. It has to be a calculus error. Well,
Yeah,
I mean, that's what they told me back in the day when I was on the committee
yeah,
anyway. I don't know who
it's
was doing that.
yeah, it's tough. Um, all right. So, um, I wanted to look at M3 specifically here. And actually, these are ones I wrote, so I'm going to go back to the hard copy so I don't have to jump back and forth between multiple inputs. All right. So this M3 right here, and I'll bring in some blank paper to take away all the distraction. So you get into this habit and you're like, oh, it's the center and the constant. And I know this is going to be centered at 4 with a radius of 3, and I'm just going to test the endpoints. And that's be the 1 and 7 again. Or maybe with this one, the center's 2, I see the 3, and I kind of forget about this 2 over here and things like that. All right. But those things actually become important sometimes. And this has a 2n on it as an exponent. And I'm actually just going to write on my copy. I would actually rewrite that. Because that's actually 3 squared, right? This is actually 3 squared to the n. So that's really 9 to the n of the denominator. And excuse me, I should have muted my mic before I coughed in your ears. Now I can kind of use that trick. I'm like, oh, okay. Now my center is going to be 4, and my radius I suspect is going to be 9. But then I could put a 2n up here, and then it's going to be the square root of 9. And so as soon as they start playing with these exponents, I know 2 to 3 minutes doesn't sound like a long time, but 2 to 3 minutes is a long time. If I asked you right now to stare at a clock like I did during the warm up for 2 minutes, it's a long time. Multiple choice, your work doesn't have to be perfect, but it might be worth setting up a ratio test and making sure, because where that 2 is going to end up, how it's going to come into play. I mean, you're gambling a few minutes of time for college credit. I would go ahead and at least see how the path is leading. And then, when you get to a point with the limit, you're like, oh, okay, it's going to be that. So it does turn out this one does have a radius of 9. It's going to be one of these 2. And so I'm either going to include the -5 or include the 13. And just a quick inspection here. And again, it's multiple choice. You guys don't have to fill in all this work, but as a mathematician, it's really hard for me not to. It's been drilled into me. So I get -9 to the n over n, and I'm gonna leave that as 9 to the n. And it turns out that can pop out, right? That's -1 to the n times 9 to the n. And that is an alternating harmonic series. It's 1 over n, which is the p series of 1, but it's alternating. So this is an alternating harmonic. It will converge. And so that was my -5. So it turns out it's A. If I tried the 13 minus 4 is 9. If I tried the 13, I'm going to get 9 to the n over 9 to the n. Over, let's see, there's that other n there, right? And turns out that that one then is just the harmonic and it diverges. I can write harmonic, I can write p equals 1, either way. So again, I'm showing more work than I need to, but if you're dealing with a free response, you need the practice, so it's worth it. I think what else I was going to say. Any questions about that one? But yeah, I would just caution about trying to shortcut these, because the ratio test doesn't take that long with some practice, and it's nice. Ooh, my favorites. What time is it? 10:40. Okay, cool. Error might overflow into the second hour. I don't care. I really want to do these. I think I got 3 of these on here. I'm going to do one, and I'm going to let you guys try the other 2. So these are really neat. They give you some information, and it's just enough to play with. So I don't know my first term at all. So this is not going to be a polynomial problem. I'm not going to be playing with the derivative, but I can clearly see the center. The center's at 1. and I know it converges at 5. So when I see these types of problems, I know they're going to be asking me about other points. I always draw a number line. So I'm going to put my 1 on there, and I know that's my center. And then I know that at 5, it converges 1, 2, 3, 4, and 2. Yeah, so there's my 5. And I know it works there. So I've got to figure out, what have they told me? Well, every point inside the radius of convergence, the function converges absolutely. Inside the radius, for less than 1, it will converge no matter what. Endpoints might diverge, might converge conditionally, might converge absolutely. So the fact that it converges at 5 means this is a possible endpoint. And that's all they've given me. They've given me the center and a possible endpoint. But that means if I go the other way 4, 1, 2, 3, 4 to -3, I don't know what's happening at -3 because this might be a possible endpoint. It might be that my radius might be 4, but this is my minimum radius. And that means everything converges inside there. And I don't know what's happening outside of that. It might diverge, it might converge. The radius might be infinite. This thing might converge from negative infinity to infinity. I don't know. But I do know that for every number in between -3 and 5, it converges. So -5 out here, question mark. -3, still a question mark because it's an endpoint. -1, that one converges. It is inside that range. And 7 is another question mark. So my choice is C again, wouldn't you know it? And then they can give, if they gave me more information, if they told me it converged, it diverged at 5, then that would flip everything. I would know everything outside diverges because it might be an endpoint, and everything inside might converge. And the only number I would know it converges as the center, because it always converges at the center. So with that in mind, I'll let you look at M5 here. Oh no, not M5. M5 is another radius convergence. Oh, that's a cool one. Let's go to M6. I feel like I'm driving British freeways. My friend Verge always talks about her paper origami that she does when she's moving these papers around. And I know Brian uses the really cool electronic pen, but I have 2 of those and they fail more than they work, and I get really paranoid. All right. So look at this one. I'll give you a chance to read it and read all the choice. I'm not gonna, I guess I'm gonna try and make myself shut up. Yeah. Also, is there anything scarier than hearing your teacher say, "Oh, I love these. These are really cool." All right. So you should have identified your center. Hopefully you got started on this. And a possible, oh, actually, we know it's an endpoint. The only place they can converge conditionally is the endpoint. Everything inside the radius converges absolutely. So I know -2 is my center. 0, 1, 2. Known endpoint. So I know my radius. Do not know if the endpoint works, but everything converges in here. And everything diverges outside of it. And we're looking for something that must be true. Well, -6. Don't know. Could it converge conditionally? Yes, because it's the other endpoint. -4. They say it diverges. No, it has to converge. Converges absolutely -6? No, I said I don't know. Okay, that's still out. And then at -7, yep, it diverges. So it's got to be that one. And then I have one more of those, and I'll give you some time with this one.
Look, the answer wasn't C.
I know, right? But I had the -6s in different slots. I don't know if that would have flown. I was doing a teacher workshop one summer. We were doing integration by part problems, and we were looking at actual exam problems. And I think we had 5 in a row that were B. And it's funny because teachers are such bad students. The teachers immediately are like, it's always going to be B. And I include myself in that, by the way, for teachers being bad students. All right. So we have I'm gonna read it to give you a little time to finish up maybe. If the power series from 0 to infinity of a sub n x minus 5 to the n converges at x equals 2 and diverges at x equals 0, which of the following must be true? The series converges at 8, the series diverges at 9, or the series diverges at 11. It almost sounds like a news story. So let's see. I know my center's 5. And I know it converges at 2. So this is another one with my minimum R. 3 to the left, so 3 to the right. It's going to converge inside that area, and 8 is a possible. Now I know it diverges at 0. Now that does not confirm that 2 was an endpoint. That means 0 is another possible endpoint. So 10 might be a possible endpoint. So I don't know what's happening in between these, because this is my max R now, because I have a divergent point. But that means everything after it has to diverge. You're never going to have a point that diverges and suddenly the series starts to converge again. So we got all kinds of data mined out of this one. So the 5 to 2 is my minimum possible, which put 8 up as a potential endpoint. 5 to 0 is possible, which made 10 a possible endpoint. And then everything past 0 has to fail because 0 diverged. So does it converge at 8? And we're looking for must be true. Could be true, but doesn't have to be. Diverges at 9. That's smack in the middle of my question mark between those two. So it doesn't have to diverge at 9. At 11, however, we have to be diverging. So 3 only. And it was C. Dang it. All right. So I'm hoping you get one of those on Tuesday because those are really cool. All right, we've got about 5 minutes left in the first session. I might go over a little bit. We may take the break a little after because I do want to talk about Lagrange error bound because it is so not scary, but it looks scary. Just looking at this slide gives me anxiety. The error approximation. First of all, and you should have talked about altering series error bound with Brian last week. I don't know if you did, but I think he was supposed to. It's just the error between your polynomial and your function. And I've used the 2 most common abbreviations for polynomials here interchangeably. I said they're equal. So you can use P sub n, and these can be in either order. It's not T's on the right, P's on the left. It's just, you can reverse them because it's an absolute value. It's just what is the difference between the actual, which is f of x, and my approximation, which is my Taylor polynomial. So it can be either one of these. When you're finding an error bound on the test, one of the things they're going to look for is the error. Sometimes they want you to say, I'm looking at the error. When they say, can you approximate? You want to guarantee the approximation to a certain value. You need to explicitly write the word error less than or equal to your expression or one of these differences. I know books use R for remainder, but R can also mean radius of convergence. It can mean so many other things. Even a capital E, I don't think on the last time this occurred on the AP exam, they accepted an E. You need to say you're looking at the error or the difference between them, because you can say it verbally or you can say it with a mathematical expression. But if you think you're talking about error and they haven't used the phrase error, bring one of these three statements into the problem, obviously with the correct, if it's g of x, or if you called it p or t, use the right letters. But that said, the Lagrange error bound, it's got its own Wikipedia page. It's an amazing page. It's hard to read if you don't have some mathematical background. But almost all the proofs of the Lagrange error bound use mean value theorem, because it's all about what's the maximum possible of change between the function value I know, my center, and the function value I'm approximating. And so that's the goal of Lagrange error bound, is what's the maximum change that could have occurred between these 2 points, and then I know I'm inside it. If I can find that maximum change, I know I'm inside that. So that's why the error looks the way it does. So they go up 1 degree. It's different than alternating series. Alternating series, you go to the next term. And if the exponents are jumping 2, like they do with sine and cosine, you go to the next term. Lagrange error bound, you always go to the next power, even if in your polynomial it would have had a 0 coefficient, because it's not going to have a 0 coefficient anymore. So you go to the n plus 1th power, and you find the derivative at some number z. We'll revisit that. Over n plus 1 factorial times x minus c to the n plus 1. Again, knowing the general term of the polynomial is powerful. If you know the general term of the polynomial, you just change the c to a z here, and then you have to remember that what that's telling me is I have to find the maximum change that can occur on the interval between x and c. And that's what that derivative is. The maximum value of that derivative, because derivative is rate of change between x and c, the maximum of that has got to be the most the function could have changed between where we're at and what we're trying to approximate. And let's see, what's my next? Now, they do tend to make this a little easier for you. There are only 4 ways they show it. And we're going to look at these and then we'll take a break. Okay, I know we're at the 1 hour mark, but I think we started a little late, so whatever. And thank you to Dennis Donovan. I'd be remiss not to point out that he was the one who gave me this and pointed this out. There's only 4 ways they've ever tested Lagrange error bound. And it's how do I get that change? How do I get that maximum derivative? Sometimes they explicitly tell you. And can I make that link hot? I think I can actually make that link hot. Nope. So if I go back to a pointer. Yeah. So I'm pulling these up on a different screen. I'll show them to you in a sec. But sometimes they just tell you, hey, the max value is this, and you get to use it. Sometimes they give you a graph and you have to be able to interpret that graph. Sometimes they'll give you a table of values for the n plus 1th derivative, and they'll give you some information about the behavior. They have to tell you it's always increasing or always decreasing, so you can pick out that max value since they're discrete points. You don't have to worry about whether it's oscillating or something like that. And that was in 2008. And then if they use sine or cosine within the function, if sine or cosine shows up in your derivative function on any interval, you know sine or cosine's maximum value is the amplitude. If there's a modifier in front, typically 1, but if 3 cosine x, the max value is going to be 3. And so here are those 4 examples. And I believe the first one is actually BC4. Look at the old fonts. Wow. So they give you a function as derivative. Wow, this stem seems really familiar. Assume f of 2 is -3 and so on. You write the 3rd degree Taylor polynomial, which we can all do after once we know that polynomial, and that's 4 points. You plug in the 1.5, and that's why I lead off with Taylor polynomials, because that's 4 points. And if you get 4 on this, you're probably beating the national average. The 4th derivative of s. Okay, and here we go. The 4th derivative is always less than or equal to 3. Now use Lagrange error bound on the approximation, and you can see it done here. There's that maximum value of 3. It's the 4th derivative, so they're dividing by 4 factorial. 1.5 is, let's see, where's the one? That's our x value. That's where we're approximating, minus our center 2, raised to the 4th. And this was calculator active, so they were able to throw it in a calculator. 2011. I don't know, Nick, you might remember this one. This one started arguments. So they've given a graph of the absolute value of the 5th derivative. And then we're going to jump right to D. There's a lot of good stuff here, but D asks for the derivative at 1/4. I'm sorry, the approximation at 1/4. So they want to, you're going to have to use, and they even say, use the information from the graph. For my 4th degree polynomial, I need information about that 5th derivative. We're doing it at 1/4. So as I zoom in on this graph, there's my tick mark of 1, there's my tick mark of 1/4. So it's between the center at 0 and the approximation at 1/4. And I don't want to eyeball that. It's actually above 35. If you choose 35, you got it wrong. But just use the 40. The 40s, use the tick mark they give you. So I know it's always less than 40. And I'm trying to show this 3,000. So I say, all right, that max value, well, I know it, notice it's less than here, not equal to, because it's under 40. So I know this error is less than 40. 5th derivative, so 5 factorial, which is 120. And 1/4, because this was centered at 0. So that's 1/4 minus 0 to the 5th. And then you can leave it here, but if you confirm it, it is 1/3072, which is less than 1/3000. But I think it is important also to point out, students could leave it here if they trust the math. If you trust you did it right, you just want to say, yeah, that's less than 3,000th. But if you go check yourself, 4 to the 5th is 1,024. The comp sci people will tell you that's 2 to the 10th and be able to get that for you real quick. And then BC3, a series on BC3. That must have freaked kids out. It has a Taylor on number 3. Wow. Again, write the 1st degree Taylor polynomial, approximate 4 points. And then also whether it's greater or less than, but still 4 points playing with that Taylor polynomial. 3rd degree, 7 points from Taylor polynomials. I love this problem. All right, and then the Lagrange error bound. And here they just tell you. We're trying to show it has error less than 3 times 10 to the negative 4th. It's 3rd degree. I need the 4th derivative. H and these 4 derivatives are increasing. So I know this is always going up. So I want the highest number on the list. It's increasing. So the 11/25 over 16 is the highest number without having to confirm it. And then you come down and that's the number you use in your bounds. And oh, I'm sorry, I take that back because we're centering at 2. Burp. Totally dropped the ball on that one. So we take the 4th derivative at 2 and we know that that's the highest value because it's always increasing. All right. And then the last one, 2004. I know this is dry as heck reading problems, but I want you to see these because these are cool. All right. Find the 22nd coefficient. We're not doing that, but realize that's why you need to know that Taylor polynomial because you don't want to go through 22 derivatives. You can build that. Error bound. We want to show, so at 1/10, right? This is that form. So I want to show my polynomial 1/10 approximation is within 1/100th. And it is a sine function. So the derivative of this is going to be cosine 5x plus pi to the 4, chain out of 5. Second derivative is going to be some trig function, chain out another 5 is going to be a 25. So when I get to the 4th degree, it's going to be, first derivative is going to be 5, 25 is going to be 5 to the 4th is my magnitude or my amplitude. So I have to do the 5 to the 4th. And I'm actually going to pull up my camera because some of you are definitely sharp enough to understand what I just said. And some of you are like, whoa, 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 whoa. So let's bring this in. So they had this, F was sine of 5x plus 4, I believe. So F prime is going to be 5 cosine 5x plus 4. And you start seeing the pattern because of the chain rule.
Say, Mark.
Yeah.
You might want to move your sheet to the
Thank
left
you.
a little bit.
Thank you very much.
Well, now I can't see it at all.
That's why we have 2 people, among other good reasons. And of course, like I said, if you pick up on the pattern, you can just jump to, oh, my fourth derivative is going to have negative 625 in front, actually positive. And so that's my amplitude. That's going to be the maximum value of that derivative. And that's why they come in with a 625 right here. So, all right, it's 11:08. It's way too late for the break. So let's take a 6-minute break, come back at 11:14 or 10, yeah, 11:14, and we'll wrap up our Taylor series.
Oh, and Mark, Mary pointed out that the fourth line should be third derivative. I think you just wrote F double prime.
Man, I'm gonna give Mary my pen. Thank you again.
Oh, she said no thanks.
Nice.
All right, 6 minutes.
All right. Yeah, I didn't put a warm up on this one because I knew the time was gonna. 2 hours sounds so long until you're in front of a group of people, and then, as we all know, 2 hours goes really quick.
Did you notice I had gotten kicked off pausing?
All right. So we're gonna. I know we're not done with Lagrange error bound because we haven't actually looked at a problem yet. I was looking through my worksheet. I was trying to find if I had a multiple choice error bound. I don't think I do because I don't think they ask it that way very often. So but I have a couple free response. I have it. So we'll pick it up while we pick up everything else. So no warm up this time. I think we're plenty warm. We're going to do, again, some multiple choice free response. And then I actually have a Desmos activity that you can do on your own that's self-checking and you can play with because I'm sure our time will bump up here against noon real soon. But so this is the last 2 sections of the CD, the last 2 sections of the course. The test is right around the corner. Extending polynomials to Taylor and power series. So now we're taking that Taylor polynomial and we're just keeping going because just like Riemann sums, just like arc length, just like volume, just like area, how do we get better approximations? We do infinite approximations and we find out if it works. And so that's where we go to infinite series. That's where our convergence tests become really important. Endpoints of our Taylor polynomials, and then of course our Taylor series. There are 4 Taylor series you have to have memorized for Tuesday. So this would be this afternoon, you memorize polynomials, the Taylor polynomial form. Tonight, before you go to bed, memorize these 4. And the first one, good news is you've probably memorized it a couple of years ago. You just didn't realize it was a series. So the 1 over 1 minus x, and this does tie to binomials. It does tie to logs. So you may have heard those, but here it is, this 1 over 1 minus x, and we can start manipulating and using it different ways. If you can ever get it into this form where you have a single numerator, and that single numerator could be like x minus 2 if it's centered at 2, but a numerator, and you can get the bottom to 1 minus a thing. Well, then the infinite geometric sum of a geometric series is the first term over 1 minus r. And I always like putting first term here instead of a sub 0 or a sub 1, because then that's dependent on the indices and whether you start at 0 or 1 or whatever. It's just, what is the first term in your series? That's the numerator. Whatever you're subtracting from 1, that's your radius, or it's not your radius, sorry, it's your ratio, because this is geometric. And so for 1 over 1 minus x, my first term is 1, my r is x, so it's just 1 times x, times x, times x, times x, and so on. And I build that series. And again, this is the way you may have learned the formula if the lower index was 1. Of course, the absolute value of r has to be less than 1. So this only works for x values that are between -1 and 1, because x has to be, now the absolute value of x has to be less than 1. And don't worry about writing that down. I have in the worksheets, which hopefully you can download from the folder. Where's my camera? I have those 4 types of the Lagrange error bound, and these are just grayed out because my printer doesn't do gray well. But those are the 4 problems that we just looked at. And then later on in the sheet. Oh, did I not print it? Oh, I thought I included it. Okay, if I didn't, I'm going to include it. I will get you a hard copy in that folder of these because I also include the intervals of convergence. E to the x is just 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, x to the nth over the n factorial, and so on forever and ever and ever. That's a cool one. Now, one of the ways to remember this one when you're identifying them in multiple choice questions, you have a positive base of e. It's always going to be positive numbers. So you're not going to see alternating signs. You will see alternating signs if this r here is negative, or in sine and cosine, you'll see alternating signs. It's not symmetrical, so it's not even or odd. It has all the exponents represented. So that e to the x, you should know, is that either the exponential growth or exponential decay graph. The other 2 you should have memorized are sine and cosine. And sine x starts with x. It's x to the 1 over 1 factorial minus x to the third over 3 factorial plus x to the fifth over 5 minus x to the seventh over 7. And in that documentation, I do promise I will provide, it will have, along with the interval, it has the general term. I just didn't want to busy up the slides with the general term. Couple things to keep in mind. Sine is an odd function. That is, it's symmetrical about the origin. If you flip it 180 degrees, you get the same graph. That was the definition of odd function you learned some point, and then quite possibly forgotten. That's okay. But that's why it's odd powers here. 1, 3, 5, and 7. It's modeled by odd polynomials because it's an odd function. Cosine, on the other hand, is an even function. It's symmetrical about the y-axis. And so it has x to the 0, x squared, x to the fourth, x to the sixth, and so on. It has all the even powers. I had a young lady a couple of years ago who said she didn't remember odd and even functions being taught when they were, but she just said, oh, sine is 1 syllable, cosine is 2 syllables. So sine is 1, that's odd, cosine is 2 syllables, it's even. That's not a great formal definition, but I've got people who are hopefully watching this who are taking the test May 4th. And if that makes the difference for you remembering it, I win, because that's, and so thank you to her for that. If
Mark,
you, yes, I saw she
on
said,
on your slide,
oh,
the
cut and paste issues. Wow. I
yeah,
saw that in the chat. I was like, I'm positive I said odd, but
you said even, but
yes,
it's written as
you're
odd.
right. I will send a correction to Aaron as well. For those of you that were watching the College Board videos, you know, I put this all together yesterday, so it's a tough run. So, and then the other thing to keep in mind is your first term, again, not to beat a situation, but I keep going back to Taylor polynomials. That first term is f at your center, and f of 0, which is sine of 0, is 0. So there should be a 0 term before you ever see a variable. Cosine of 0 is 1, so we have to start at 1. I had mentioned the Ben Goldstein chapter before, and he does his first Taylor polynomial he does in the book is sine x, and then the way he develops cosine x is real natural, that cosine is the derivative of sine. So if you just memorize sine and then take the derivative of every term, you build the cosine one. So if you're really, pressed, and that's a way to remember as well. And I think that's a cool connection. Plus, it also leads into the fact that your intuitions of all the calculus you've been doing since August, and possibly the previous year, if you do an ABBC sequential course, all your derivatives, integrals, intuition works with these series. And so I am allowed to actually take the derivative term by term to generate the series of the derivative. So In fact, if I took the derivative of this, I should end up with the opposite of that, right? And that's my next thing is because the last section in the CED is using those 4 functions to build other functions. And trust your intuition. It really will work on this. You can use all those above to create new functions. You can add 2 series together. You can subtract them. You do have to be careful with multiplication division because you do have to, I say trust your intuition, but I'm going to say trust your good intuition. If I'm multiplying 2 series, I can't multiply corresponding terms. I actually have to lay them out and start doing distribution and then combine my like terms. Generally, when they do that, they only ask for a second or third degree. So you just lay out enough until your powers get higher than that. And then you can stop. And then again, we can integrate and differentiate. And the radius of convergence stays the same when you do that, although endpoints need to be retested on each cycle because sometimes the endpoints work and sometimes they don't. And I'm actually going to look at BC6 and I'm actually going to give you time to read this and look at this one. I'm not just going to read it to you like I did with those Lagrange error problems. So I don't want you to see the answers. Let's see. Here we go. And I'll just hide the answers with my camera. All right. So this is the Maclaurin series for a function f is given by this series from 1 to infinity of -3 to the n minus 1 over n times x to the n, which expanded is x minus 3/2 x squared plus 3x cubed minus so on the general term -3 to the n minus 1 over n times x to the n, which of course is the summation, the next to the same term next to the sigma, plus dot dot dot. It converges to f of x for the absolute value of x less than r, where the r is the radius of convergence of the Maclaurin series. And then it asks you to use a ratio test to find r. I'm actually not going to do that part. We've done a ratio test. I can actually show you that. It does end up being, I believe, 1/3 because the limit ends up being -3x. And then the absolute value of that is 3x. But that's 3 points for that ratio test. I want to talk about the other 6. So write the first 4 non-zero terms of the Maclaurin series for f prime, the derivative of f. Express f prime as a rational function for the absolute value of x less than r. And write the first 4 non-zero terms of the Maclaurin series for e to the x. Use the Maclaurin series for e to the x to write the third degree Taylor polynomial for g of x equals e to the x times f of x about x equals 0. And I'm going to, again, mute myself and give you a minute or two to get started on those. And if you get stuck in B, where you think you got a part of it and then you're not sure what to do next, jump to C. This is a very great for May 4th. You can come right around. Some of you are taking it May 24th, I know, or June 9th, but I think June 8th actually. Question 6. It's the last one. You're 3 hours and 45 minutes in. Don't be afraid to jump around. Find that part you can do. Go get the points you can get. So, like I said, I'm going to shut up and let you do that. Although some of you are probably working already. All right. Scoot this up. Scoot my paper down. Got all the relative information I need. All right. So they asked me to find the first 4 non-zero terms of f. I didn't label this. So f prime. And like I said, intuition's great. And you can take the derivative of the general term and then build it. But I can also just build right off here. Derivative of x is 1, 3x, because 2 times 3 halves is 3. And then plus 9x squared. And then I don't have the fourth term. I know it's going to be minus. And you can get that fourth term 2 different ways. I can do the derivative of this. X is the variable. We're only taking the derivative with respect to x. So this is just along for the ride. Bring down the n minus 1. So I could do thought bubble over here. And negative is supposed to be on the inside, wasn't it? Negative 3 to the n minus 1 is a constant. X to the n minus 1, and then those cancel. And I could plug in n is 4 into that. But I think what most students did, what most people do is they look at this pattern and they go, ooh, it's times negative 3x times negative 3x, so times negative 3x. And actually, I shouldn't say most. I say it's about equal. Probably half the people do this and half do that. But that's your first 4 terms. And the student who noticed I'm multiplying by the same thing every time actually has a leg up, because this rational function idea, it isn't very often that we ask students to find the function or to find the actual sum. When you're asked to find the actual sum, it's almost always a geometric. Rational function, it's either geometric or it's a manipulation of sine e to the x or cosine x. But I am multiplying by negative 3x every time. So that's a common ratio. And this thing equals that sum of the first term over 1 minus r if it's geometric and r is less than 1. But they said in the little question stem, we're only giving the answer for numbers inside the radius of convergence. So I don't have to worry about that r being inside the radius of convergence. They've told me I'm going to stay within it. So my first term is 1. My r is negative 3x, and I can just leave it like that. Or if I want to clean it up, it's 1 over 1 plus 3x. And so that is f prime. And that point was actually a very hard point for students to connect to. So if you see that and you can do that, good on you, and good on you for Tuesday. C, and you'll notice C, they just asked right off the bat, give the first 4 terms of e to the x. This happens. They'll ask for the first 4 terms of e to the x, they'll ask for the first 3 or 4 terms of sine or cosine, and it's worth points. So that's why this evening I want you memorizing those after you memorize the Taylor polynomial. So e to the x is 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus dot, dot, dot. I put the dot, dot, dot to make it equals. If I don't put the dot, 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 probably should put squiggly equals. I don't think that's going to cost you a point, but it's just good communication. And then I'm going to remind myself that f of x was x minus 3 half x squared plus 3x cubed. Because the thing I didn't write down is which Taylor polynomial they want. They want, yeah, the 3rd degree Taylor. Lost my camera. There we go. So I want the 3rd degree Taylor. And it said to use e to the x. So they want me to take e to the x, which is 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus dot, 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 and multiply it by x. And that is not a polynomial yet. It's not even 3rd degree. I think I see a 9th hiding in there. So I need to start distributing. 1 times x, 1 times 3 halves x squared, 1 plus 3x cubed. The next term, I could find it. but it's x to the fourth, and I only want the third degree Taylor polynomial. So I'm going to stop there. And then x times x times 3 halves x squared is negative 3 halves x cubed. Again, I get an x to the fourth term, so I'm not going to include that. Walk on down with my x squared. X squared times x is x cubed over 2 factorial, which I'm just going to call 2. Here I get x to the fourth, x to the fifth, I'm done. This x to the fourth, x to the fifth, I'm done. So these are the only terms less than third degree. So I'm not going to label it here, but this is my third degree Taylor polynomial right here. Now, can I leave it like that? Unfortunately not. We harp on the fact that you don't have to simplify in the exam. You don't have to simplify algebra or numeric answers unless specified. Unfortunately, asking for a Taylor polynomial is a specification because a polynomial is defined as a set of terms with distinct degrees or distinct powers of x. And I have multiple powers or multiple terms with cubes and squares on them here. So I do need to gather those. So I have 1x, and then I have negative 3 halves plus 1 x squared. That's these guys. And then my cubes. 3 minus 3 halves plus 1 half x cubed. Now, that answer is done if I want it to be, because that is a single coefficient, not numerically simplified, but it's a single coefficient with x's to distinct powers. Of course, it's not that hard to clean it up, and that's what they're going to do on the answers, right? That's 2x squared, 2x cubed, sorry. But yeah, this is kind of there, and then these two are considered the polynomial. And if I see how I did, because I haven't worked this problem this year. All right, I got 3 points on part B. Notice the first 2 points were for the first 4 non-zero terms. So I suspect that when I got these 3, I had the first point, and then that's my second point. And then the third point was for the rational function. And then in part C, 1 point for writing the first 4 terms of e to the x. That is the last section of the last free response of a 4-section test. 3 hours and 45 minutes after you started, counting the 10-minute break, maybe closer to 4 hours, you can get a point for writing down the first 4 terms of e to the x. Never stop reading. Number 5 is a disaster for you. Go to 6, read all the parts, find those points, prove to them you know enough calculus to take the next course. Right. 2 points for the Taylor polynomial, and it looks like I did get it right, so yay for me. And then when there's 2 points there, I'm sure there were ways to get 1 point, depending on whether they included extra terms or there was a simple arithmetic error, but the setup was correct, things like that. I will say they dictated a method, and it said use. Pay attention to the word use on Tuesday. If you have a separable differential equation and they say use separation of variables, even if there's other methods, if you've taken IB, you probably know about integrating factors. Sometimes you can actually do it the way we did the very first warm-up back at 10 o'clock. But if it says to use a specific method, you're not going to get full points without that method. And it is possible to build this series, to do the first derivative, second derivative, and third derivative, and build it using the Taylor polynomial formula. However, if a student did that, they only got 1 of the 2 points at the end. They didn't get both because it said you had to use e to the x. They were trying to find out if you could multiply series, if you knew you were allowed to do that. And if you haven't demonstrated that skill, then you haven't earned the point they were trying to test you for. So, you know, pay big attention to that word. It's going to mean a lot to you. And I'm not going to do BC6 from 2018 because I want you guys to start looking at some other ones, but I do want to show you what that looked like. So here's another one. So they gave the function x times log of 1 plus x over 3, and they should, up here they gave the Maclaurin series for just log of 1 plus x. So when they asked for the first 4 terms down here of this function, you have to figure out what have they changed. And they replaced x with x over 3. So I would go in and replace that x with x over 3. This becomes x squared over 9, x cubed over 27, or you could leave it as x cubed over 3 cubed, whatever. Plug x over 3 into all of those, including the general term, and then they multiplied by x. Multiply every term by an additional x, and that's how you build it. It's the algebra and the calculus meeting up, and as long as you don't break any rules, you're okay. All right. So let's go back to some of these practice problems. I think it's 8, the first one. Oh, yeah. So I'm going back to M8. And it says, let f of x equal the integral from 0 to x of sine of t dt. Which of the following is the first 3 terms of the Maclaurin series for f of x to the 5th? And be warned, sometimes they test 2 skills at once, or two knowledges. So I think where I would start with this, because it's a Maclaurin series, because I see sine t, I think I would actually start with sine x. And this will be sine x is equal to, let's see, it's sine is 1 syllable, so we're starting with the odd powers, x to the 1, x cubed over 3 factorial, x to the 5th over 5 factorial, and so on. And then f is the integral. So we're doing the integral of this, so the integral of sine of x. And oh, I guess this is where the t's become important, huh? I guess I could have done that with t's. The horror. I'm going to substitute t on the fly. Antiderivative of x be 1 over, that's just, yeah, 1/2, right? 1/2 x squared. So in this case, 1/2 t squared minus t to the 4th, 4 times 3 factorial. Oh, it's picking up speeds. 5 plus 1 is 6. 6 times 5 factorial, and so on. Evaluated from 0 to x. Now I get to plug my x's in. 1/2 x squared minus x to the 4th over 4 times 3 factorial. Oh, and I misspelled x there, or t. X to the 6th over 6 times 5 factorial minus, and then when I plug 0 in, I get a whole bunch of zeros, like infinite zeros. All right. So this is my f of x. Now they want f of x to the 5th. So I simply plug x to the 5th in each of these. So this will be 1/2 x to the 10th. 5 times 4 is usually 20. Oh, and 4 times 3 factorial. That's cute. When I start looking at these answer choices, 4 times 3 times 2 times 1 is 4 factorial. 5 times 6 is 30. 6 times 5 times 4 and so on is 6 factorial, and so on. And so we get B. And that's a problem when you first look at it, you might have no clue what to do. This is why I always encourage people to keep their pencil moving, keep their pen moving. I see the word Maclaurin, I see the word sine, lock onto that, get that Maclaurin series for sine, and then now I'm integrating it, and now I'm plugging in x to the 5th. It's just do what you know, and you're going to be okay. All right. I'll give you some time to try to do 10 on your own. So you're given f of x with that general term and trying to find f prime. Okay. All right. I think I have a plan for where we're going for the last 15 minutes, which is good. All right. So again, there's two perfectly legitimate ways to start this. I could start by trying to find the general term of f prime. I wouldn't necessarily write equals to. I don't want to worry what happens if this n equals 1 or n equals 0. I'm just gonna, I could come over to the side and do, all right, 3n times x to the 3n minus 1 all over 2n plus 1. And that'd be my general form of my derivative, because again, n is a constant within this relationship. N's changing a lot for the summation, but for the function itself, it's a function of x. So I only take the derivative of the x term. So 3n's a constant within that function. And I bring down 3n minus 1. And this is a cool way to do it. I think as a student, I was more likely I would have just plugged in 1. Again, x to the third, 2 times 1 is 2 plus 1. And plugged in the 2 and got next to the 6th. 2 times 2 plus 1 is 5. And then realize, oh, the top's geometric. It's going up, the exponent's going up 3. The bottom's arithmetic. It's going up 2. Right. And then just take the derivative of that. And I'm actually done if I really trust myself on that first term, but I don't. So this is x squared plus 6/5 x, 9/7 x to the 8th. If I want to check the fourth term, I could plug in 4. 3 times 4 is 12, minus 1 is 11. And then 2 times 4 is 8, plus 1 is 9. 12 over 9 is 4/3. So that actually, the general form confirms that one really well for me. All right. I want you to try to do number 11. We're going to do 2 more multiple choice, and then we are going to go back to a free response and pick up a Lagrange error, because I know I talked about it, but I didn't actually demonstrate one. So. I need to go back and look at the source of the problem I stole this from, because it's weird that that function isn't named, but I wonder if it wasn't named in the original or if that's my typo. All right, so again, where to start? Well, I latch onto the one of the 4 functions that I know. I latch onto that and start writing what I know. That's 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And then I plug in the x squared. X squared squared is x to the 4th. X squared to the 4th is x to the 8th. And then x squared to the 6th, x to the 12th, and so on. And then I subtract the 1. And I'm just going to subtract that 1. So it's going to be everything after it. So that looks like none of the above. Or is it D? Oh, that guy's little. I think it's D. I don't feel like I should check with Mary right now. So for some reason, I'm feeling like I goofed that, but x squared to the 6th is x. Yeah, feel okay. You're slow on this one. Okay. Well, check me, because I'm feeling like I said it was something else yesterday.
Well, either we're both wrong or we're both right.
Excellent. Good. I feel I'm okay with either of those situations, actually, because you don't need a 108 on the exam to make a 5. So.
That was something I used to say to my students often. Well, I would still get a 5.
Yeah. If you get a perfect score, you get a letter and the government starts watching you. Okay, so the second part's false, but you do get a letter. Yeah, it's been a while. Okay, D's great. So, and then, like I said, we're skipping some of these, and I am going to get those solutions up to into the folder for Aaron, but I think 13 is a cool one. So, and 13 is based on a recently released one, and that's like within the last couple of years. So I wanted to get a chance to look at this one because this is different. So it says a function f has a Maclaurin series given by 4 minus 2x minus 6x squared plus 3x cubed, and so on. And the Maclaurin series converges to f of x for all real numbers x. If g is the function defined as g of x equals sine of f of x, what is the coefficient of x squared in the Maclaurin series for g? And I'm actually not going to give you that much time to look at this one because this is a tough one. And I think with the time we have, I think it's better just to in case there's one on Tuesday, let's talk about how to attack it. So I don't want to build this one the same way. I don't want to, because I don't want to plug all these into the x for sine of x. That's a ridiculous task. I don't want to have to try to figure out what this function simplifies to. If it does, it probably doesn't. What I want to do is build what I know. And for the coefficient of x squared, going all the way back to our beginning, I know the coefficient of x squared is going to be, we're talking about g, is going to be g double prime at our center. It's a Maclaurin series. It's going to be g double prime at 0 over 2 factorial times x squared. That's my coefficient. So what I really want is the second derivative of g at 0. So g of x is sine of f of x. G prime of x then is cosine of f of x times an f prime of x. That's chain rule. Derivative of sine is cosine. Interior is not just an x, so we chain out an f prime. And then, oh lordy, g double prime is a product rule. And this happened on an actual exam. Those released practice exams are exams students had to take. So I'm going to do a product rule. Derivative cosine, negative sine, f of x, times a chain of f prime of x, times the f prime of x that was already sitting there. Scoot my paper over. Plus cosine of f of x times the derivative of f prime, which is f double prime. Well, that's awesome. So now I need to know all of these at 0. And I lost a parentheses. So they did give me this other, and there's not a lot of distractors on multiple choice. Generally, all the information they give you is useful. So this is my f. Right? They said this converges to f. So f of 0 is 4. And f prime of 0 is negative 2. And f double prime of 0 is not negative 6. It's negative 12 over 2 factorial, because that is the second derivative divided by 2. And then there's the third derivative, which I don't need, but it would be 18. But now I can come in and I can go plug all of these in. Negative sine, f of 0 is 4. F prime at 0 is negative 2. Still negative 2. There's 2 of them there. Oh, that parentheses came out as an F. That was weird. Plus
Hey,
cosine.
Mark.
Yeah. Yeah.
Shouldn't f? Never mind.
Okay.
I see what you did there. Never mind.
F of 0 is 4, and I love Lena's comment. And f double prime at 0, we decided was negative 12 over 2. Wait, I did that wrong. F double prime is negative 12 because that coefficient.
Yeah, that's where I was.
Thank you.
And yeah.
Yeah, it's that, right? So that's going to be a negative 12. And so cleaning this all up, negative times negative, 4 sine of 4 minus 12 cosine of 4, which should be a choice, right? Oh, but Oh my goodness, what an evil, whoever wrote this, I want to know who wrote it because it's so cool. But at the same time, like, how many kids did this? All right, I'm so happy I got my second derivative. I almost circled B, but I'm looking for the coefficient. I've got to divide it by 2. So it's A. And for a student, and those of you in the room that are students, that's a tough one. That's a problem that's going to be, in a multiple choice worth 1.2 because they multiply it up to 54. That's 1.2 points that if you get it, it gives you a leg up on some other people because that is intense. And if you feel comfortable with that problem, you do a couple of these. If you go find that practice, go ask your teacher, check the 2019 test. Go do another one of these. If you get comfortable with this, not only are you comfortable with this, you're now comfortable with coefficients. You're comfortable with reading derivatives off coefficients. You understand where the rules are coming from. It's a really rich problem for you to use as a learning device. And so I encourage you to go find your teachers. It's on, I believe it's the 2018 or 2019 BC test that was released, has a similar problem. It's not a trig function, but it's very similar. And it's 11:55. Okay, we're gonna jump to the Lagrange error just so that we've done one. And then I want to talk to you about the Desmos activity that's there that you can use to practice this weekend, and also just open up for if someone has questions. There is a typo on my copy. It has a negative. It's supposed to be negative x squared there. I'm not going to do this because you were told. It says show the second derivative is this. If you're asked to show, you're just doing implicit differentiation, carefully showing all your steps. You plug dy dx in when you get a y prime, and you can show that this will lead to that second derivative. This says, let f of x be a particular solution to the differential equation, which is the given one, with the initial condition going through the point 0, 2. Write a second degree Taylor polynomial for f about x equals 0. Well, this is the thing we started with. F of 0 is 2, so my polynomial is going to start with 2. Plus, I'm going to plug the point 0, 2 in here. Actually, I was going to skip it, but it's so easy, we're going to do it. So it's going to be f of 0 plus f prime at 0 times x. How about that? Are we centered around 0? Yeah, about x equals 0. See, I can learn. I checked my center this time. F double prime at 0, x squared. So f of 0 is going to be 2. 0 over 2 is 5. And then the second derivative they did give me, even though I had to verify it. If I couldn't do part A, I can still use it down here. Y is 2. 4 x's are both zeros. So that's 4 over 8, which of course I could write as 1/2 if I didn't if I trusted myself. But at the end of 2 hours, I'm writing it. That's my Taylor polynomial. And then it says, for this function, it is known that the third derivative is less than or equal to 2 for all x's in the interval between -3/4 and 3/4. A student has found an approximation of f of 0.2 by using this function. So we're not having to, but they put point.
Wait,
Yeah.
Mark, Mary's got something else. And her thing is, isn't there an extra 2?
That too? You mean this too?
Yeah, that too.
Man, I might be making a 4 today.
You'll still get college credit.
Yeah, thanks. It's been a long week. I'm sorry, folks. All right, so we're plugging in 1/5. 2/10 or 1/5. Some student has done that. We just want to show that that value they found differs from the actual function by less than 1/200th. So we are looking at it in a Lagrange error bound. And again, notice I'm not using any of the information from the previous parts. They said they're using that model, but I don't have to go find it. So I know my error, which is equal to this difference, is less than or equal to, and it's the second degree Taylor polynomial. So I'm going to use my third derivative at some z. And we're going to divide that. Thank you. I saw the chat. Divided by 3 factorial, because again, we're going up 1 level, and this is the second degree. So 3, 3, and then x minus c. My x is 0.2, my center is 0 to the third. So we want to show that that is less than 1/200th. Well, I have to maximize this, but I know it's always less than or equal to 2. So that's going to be less than or equal to 2 over 3 factorial, which I guess we can call that 6. I did mention already that's 2/10 or 1/5. And now these simplifications are not necessary. If I lift that as 3 factorial and that is 0.2 and claimed that that was less than 1/200th, it's going to be taken because we don't have to simplify it. You're just trusting the math. But I like to show it because I don't trust myself. 5 times 5 is 25 times 5 is 125 times a third. And I'm going to take this off so I can write equals. This is less than that, which is equal to this. Equals 1 over 375, which I believe is less than 1/200th. And then I have said, and I've said this on the AP Live videos as well, they don't read crossed out work. So if you do this just to check, like, okay, I got a number that works, but what if I made a mistake? Do that to confirm for yourself and then say, no, reader, I want you to read that. And that's fine. We are right up at time. I do want to show you the last slide. Come back over. I lost my mouse. There we go. If you go to Desmos and type this in, and teachers, I will have Aaron put a link in for the teacher version of this. It is a manipulation of series card match. And I'm going to go there and start one. Hey, it knows my name. And the yellows are series, and I always like to sort first. The pinks you'll see are the names of the functions. And the blues are the expansions. Oops. And if you're working on a smaller device, these are really tough to do on phones. I originally had this with 12 families up here on screen at once, and it was a nightmare. But if you're working on a phone or a tablet or even just a 12-inch monitor on a Chromebook or something like that, you can, if you do Control minus, it shrinks the size of the cards. And then if you click a card, they blow up when you click them. So that makes it a little more manageable. Of course, if you're just getting to be, you know, half a century old, you need to click them to read them anyway. That's what I do. And you can match these anyway. Some of you might know the general terms real well if you've been working on these for a few weeks or a few months. Some of you might want to start plugging ones in and match the blue to the yellow first. I like to find the ones I know, like e to the x. There we go, boom. And I'm going to click those together because e to the x is 1 plus x squared over 2 and so on. And then look for ones maybe they haven't manipulated as much. E to the negative x, so that's just going to change the odds to negative. So maybe that's that one, and so on. And you match them all up, and you click, and then I'd have to find the ones that go with these. So I think this big monster one, I think that's e to the x. And then when you have them paired up, you can also, or tripled up, you can hit the arrow to collapse them. And then when you hit next, you say, check my work. And this slide will tell you, it says, not yet, keep trying. But if they were all right, it would say, great job. And then you can go to the third slide, and there's another set. And this one has the trig on it, it has the sines and cosines on it. And so that's just another practice. So maybe after you memorize these things tonight, you can do it tonight, or you can do it tomorrow morning, you know, with your orange juice or whatever. So I hope that all helps you. I hope we've had a decent 2 hours. Thank you, Mary, for coming and being my official checker. I'll have to make sure you come to my next one of these because it was very helpful having someone checking my arithmetic. And Monique, thank you for doing what you were doing because all the behind the scenes stuff is unbelievably helpful. And
I'm muted. Thank you, Mark.
Oh, there you go. I was like, I guess I can read the slide.
Thank you, Mark. Thanks everyone for joining us. I'm Monique Rice, and Aaron Timmons is our math content director who just joined us. Hey, Aaron. We're wrapping up now. You'll find the handouts and recordings at the bit.ly links at the bottom. Good luck next week or whenever you're taking the AP exam.
Yeah.
Bye, everybody.
Bye.